Dynamic RAM or DRAM is another type of the RAM. If you remember, the previous one was called SRAM or static RAM. The basic principle for the operation of the dynamic RAM is that storage of the information is done on the capacitors. While for the SRAMs, we had the information stored on the latches. So here the capacitors are used in order to store the information. Depending on the amount of the charge stored on the capacitor, we will have the 0 or 1 logic value. A transistor is also used as a switch, which helps the capacitor to be charged or discharged in order to store the information. In the next slide, we will see the circuit, the hydraulic analogy, and the logical model for the dynamic RAM cell. In figure A, in part A of the figure, you can see the electric circuit that we have for a single cell of dynamic RAM. So basically the capacitor that you can see here with C is the charge storage element where the information is also stored in the form of charge. And the transistor, which is here and is denoted by T, is used as a switch. So you can think that it is indeed similar to the select line that we have for the schematic of our model. So you can also see the analogy here. B is indeed the data line that we want to store, the data that we want to store in the memory cell in the form of 0 or 1. And C will be the actual data which is stored in the dynamic RAM cell. On the right side of the figure, you can see the hydraulic analogy. Let me focus on a single part and then I will explain you the different parts. So here, with the valve that you see here, we are modeling the transistor. The small tank on the right side is used to model the capacitor. And the bigger tank on the left side is modeling our data input. Whether it's in the form of 1 or 0. Okay? And this holds for all the parts on the right side. Then what we see in this B section is that we see that the pump is closed. Okay, so over here the pump is closed. For part B, the pump is closed, and we have the value of 1 stored in our tank or in our capacitor. So you can see that it is filled almost completely. So this means that we have the value of 1 stored. So 1 is stored. In part C, over here, we see that still the valve is closed. Okay, so we don't read or write into the memory cell, but we see that there's no liquid inside the small tank, and it means that we have the value 0 stored in our memory cell. When we want to read or write into or from the memory cell, we need to turn on the pump, and that's what happens in part D and E for writing. So over here you can see that the pump is open. That's why the pipe which is connected to the valve is highlighted in blue, meaning that there's liquid inside. So this means that the valve is open. Valve is open. And since we want to write 1, on the input data side, the big tank is filled with liquid. So over here, the tank is filled almost completely with the liquid, and then the the valve is opened, and as a result we have the flow of the liquid from the bigger tank to the smaller one. So the level of the liquid in the small tank will be high, okay, somewhere around here, and it means that we have written the value of 1 into that. While if we want to write the value of 0 into our tank, into our small tank or into our capacitor, what we need to do is to empty the bigger tank, and you can see it over here. So the level of the liquid in the big tank is quite low. The valve is open, and therefore if the smaller tank was filled with 1 beforehand, we would have the flow of the liquid in this direction such that the level of the liquid in the smaller tank drops, okay, and it means that we are restoring value of 0. If it already had the 0 value stored, then the opening of the valve wouldn't result in the movement of the flow of the liquid between these two tanks, because for both of them we had the level low, and therefore as a result the final level of the liquid in the small tank will remain as low or 0. So that's what we have for writing. But when we want to read from the small tank, let's say, okay, we want to read from the memory cell, we again need to open the valve. That's what you see here. When we want to read the value from our tank, we just open the valve. For our bigger tank, we have an intermediate level. Let's say the initial level of the water was here. And now when we have the value of 1 stored in the valve, if we open stored in the small tank, if we open the valve, we will have the flow of liquid in this direction. So the level over here will decrease a little bit, and the level here will increase a little bit, and that will tell us that we have read the value of 1. On the other hand, if we want to read the value of 0, that's what we have here. And again, assuming that the initial level of the liquid in our tank was somewhere around here, by opening the valve, we would have the flow of the liquid in this direction. And as a result, the new level that we have for our big tank will be lower, while for the smaller tank we will have the level rising a little bit, okay? So referring to what changes we have in the bigger tank, we would say that we have read either 1 or we have read either or we have read 0 from our memory cell. However, you can see over here that by reading the value from the memory cell, at the same time we are modifying the content of the memory cell a little bit, okay? And if we do so, then especially if we do it more than once, then the level of the liquid in the small tank might be some value which doesn't correspond to either 1 or to 0. That's why this kind of reading is called the destructive reading, because we are kind of destroying the stored information, and therefore after reading we would need to restore the information. Yeah? In order to restore the information after reading, if we know that we have read 1, then we just write 1 into it again. If we have read 0, we write 0 into it again, and we already know how to do it through here. Over here in the part H, you can see the dynamic RAM cell model. In the model, we are using the D-type latch, which receives the clock, the C input from the select. It receives data input through the B channel, and then we have a three-state buffer here to pass the value which is stored in the latch into the outside world, and we do it through the three-state buffer in order to be able to connect the output of multiple cells to each other. Okay, so I hope this had given you some understanding in terms of how the dynamic RAM works and why do we need to refresh the restoring it, why we need to restore the information after doing the reading. And one more thing here is that we need to keep in mind that after storing the information in the dynamic RAM, after a while, due to some leakages in the circuit, the level of the charge in the capacitor might change, even though the actual value that we have stored in the memory hasn't changed, but due to the leakages, the amount of the charge stored in the capacitor might change, and as a result, after a while we might not have the proper amount of charge on the capacitor. For that reason, because of the leakages, we would need to have some refreshing scenario for our dynamic RAM system. If we are using the dynamic RAM, DRAM, we need to do restoring of information after doing the reading, and we also need to refresh once in a while the content of the dynamic RAM such that we don't lose our data. So here you can see how the bit slice of a dynamic RAM memory looks like. Basically, it is quite similar to the SRAM, apart from the fact that the schematics that we have for the dynamic RAM are different than the ones for the SRAM. Other than that, we just have put all the cells one underneath the other one. They all receive the select input from the word select, the structure for enabling the chip, the slice, reading and writing into it, providing the input data are also similar. The output of the dynamic RAM cells are connected to each other using the three-state buffer, which is done in a similar way. And then the data out is also taken in kind of similar way, apart from the fact that here we have the sense amplifier, which is used to amplify indeed the small changes that we have at C into 0 or 1. The symbol is also quite similar. So the difference, indeed the main difference here is that we have dynamic RAM cells instead of static RAM cells. So that's probably the only difference that you could see over here. Apart from that, we have the data in, data out, bit select, and read write inputs to the symbol, similar to what we had in the SRAM case. However, one thing to keep in mind is that for the dynamic RAM, each cell is constructed using a transistor plus a capacitor. While for the SRAM, there's no capacitor, but the number of the transistors which are used are more. So for that reason, the dynamic RAM is in general cheaper than SRAM. Okay, the cost of a single cell for dynamic RAM is smaller than what we have for the static RAM. For that reason, and also the area which is required is also smaller. For that reason, the big memories usually are in the form of dynamic RAM. One more thing to keep in mind is that since we are going to build big memories using the dynamic RAM, then the address lines would be also big. In order to keep the number of the pins, input pins to the dynamic RAM is small, a specific consideration is made for the address. So the address is divided into the row and column as we had in the form of a matrix for the SRAM. So we need to select a row and select a column. So which row, which column, to specify a specific a given, let's say, element in the memory. However, the row address and the column address in this case are provided in the serial form. So from the address line, we first provide the row address for one clock pulse, and then we provide the column address for another clock pulse. So in this way, instead of having, let's say, 20 address lines, for example, 10 of which would be for the row and 10 for column, let's say, instead of having this, we can have only 10 address lines and then pass the row and column address in series, one after the other one. Over here, you can see the timing for the dynamic RAM reading process. The clock is provided by the CPU. Initially, we need to provide the row address for one clock pulse and then column address for the next clock pulse. The row address struct goes to 0 during the time in which the row address is provided, and then the row address will be stored inside a register. And then during the time in which the column address is provided, the CAS, the column address struct, will go down, and the content of the address will be stored inside a register, okay, in order to have them for the later users. Read-write, in this case, since we are doing the memory read operation, is kept at 1 all the time. So it's always 1, meaning that we are going to read. And after the 2 clock pulses, the output enable has gone to 0, meaning that we want to enable the output. And after a while, the data is made available for the rest of the circuit to take it, yeah, for the CPU to take the memory, to take the data from the dynamic RAM memory. And then once the reading of data is finished, output enable goes back to 1, CAS goes back to 1, and RAS, the row address struct, goes back to 1, and afterwards we will be able to perform the next operation on the memory, either to read or to write.